Hello everyone, thank you for coming to this talk. I'm Pradeep. I work as an SRE as part of my day job. I'm particularly interested in any databases. And today we will be looking at a stream processing system called Riemann. And it's written by someone you might be already familiar of. His name is Kyle Kingsbury. He writes a lot of blog posts on distributed systems, and he has built something called Jepsen testing. It's a distributed system verification tool. The main agenda is because I feel like Riemann is not well known in the observability community, and I thought like it will be a good opportunity to speak about it and see how Riemann leverages most of the functional programming aspects to build a unique monitoring solution. Let's start with a basic introduction. Riemann is basically an event processing system designed specifically for a particular domain. The domain here is metrics. It's built in Clojure. For those who don't know, Clojure is a Lisp dialect built on top of JVM. One of the very neat feature of Riemann is that its configuration is actually a Clojure code. And this brings a lot of advantages which is not present in other monitoring systems, I would say. We will look more into it in coming slides. It's built on top of Netty and Protobuf. Netty is basically an asynchronous event-driven framework for building fast network applications, and Protobuf is just a data serialization format. Riemann is basically a transient system. That is, it doesn't persist anything itself. If you need to persist your metrics and events, you need to actually store them in a third-party integration tool like whatever you can think of: OpenTSDB, Graphite, Elasticsearch, ClickHouse. Then one of the unique features about Riemann is it supports MTLS, where you can basically use the TLS certificates for doing the authentication. So both the client and server presents the TLS certificate and they can authenticate with each other. Next, let's look at some of the core concepts in Riemann. There are three main things in Riemann. First of all, Riemann event. An event is basically a signal that something has changed in the system. If you attended the earlier talk, I think in Prometheus ecosystem, it's called sample or data point. Then the next is an index. Index is basically an in-memory data structure which Riemann maintains for all the latest events so that it can directly query the index and return the latest data. Stream is basically a group of events which are flowing together from one unique node. So a stream is just a group of events. Let's look more into an event, how an event looks like. So event is basically a Clojure map. Clojure map, there are most of the fields in this event are as present in any monitoring solution, but I would like to go look into a unique field called TTL, which you will not find in other systems. TTL is basically how long that event is valid for. We will see how Riemann uses this TTL field in further slides. Then there is something called description. Description, as the name suggests, is just a description about the metrics. Some people use it for storing, let's say, a stack trace. When an exception happens, that stack trace can be stored as part of description. So it depends on the use case. Next, look at the Riemann index. Riemann index is basically an in-memory data structure. It's an in-memory hash map which Riemann maintains. It's nothing very big. It's just a lock-free implementation of Java's concurrent hash map. This hash map, the key of this hash map is basically a host and service key pair, and Riemann event stays in the index up until the TTL. The TTL, which I showed you earlier, is that decides how long the event will stay in that index. And once the TTL expires, that is considered as an expired event. Then Riemann does some processing with those expired events. And lastly, Riemann dashboard talks to the Riemann index via Riemann APIs and display the data. Next, let's look at the Riemann stream. Riemann stream is just Clojure functions, which takes an event and does some processing with those events. The child streams are also just Clojure functions, and when an event flows through a set of streams, it's basically a series of function calls. This design has some benefit because in any programming language, all this data remains on the stack. So anything which is operating on the stack variables are very fast. Also, JVM does some kind of compile time optimizations like inlining to make the things even better. And streams are since streams are basically functions, it has the advantage that you can basically build anything what you can do with any programming language. So you can split a stream into multiple streams, merge multiple streams into one unique stream. You can filter events and anything you can think of. We'll look more into it. In the top is basically a very simple Riemann configuration where we are just printing all the events in a stream to std out. The bottom shows an example output. This is the output from a standard output. Here we are trying to do some filtering. Many a times you want to do some operation on a subset of events. This is where, in this example, we have a where clause. Where is basically the stream name, you can say. And we are filtering events based on two criteria where the service name starts with Postgres and the state is critical. And all the events which gets filtered out of this is passed to a child stream. And this child stream is basically sending email to an email ID. If you look at the where stream, the first argument is a predicate, and then it can accept any number of child streams. So the predicate decides how to filter the events, and then it passes all the filtered events to all these child streams. So you can send a Slack message, you can send an email. Next is basically we are looking at how a stream is splitted into multiple streams. By default, any Riemann stream actually splits the events into multiple streams. So here we have events which are actually getting copied to two child streams. One is email and another is the Slack message. This is an example of how you can merge multiple streams into one. Let's say there are events coming from all the hosts in your data center to Riemann. Now you can merge all these streams into one. So in this case, let's say we want to know how many hosts are sending metrics to Riemann. So we are basically using Colliers operation and then doing count to figure out. This is a bit of functional programming. I hope it's not too difficult, but this shows how you can leverage the functional programming paradigm to build a unique monitoring solution. Now let's look at how you can send events to Riemann. One way is basically you can integrate the sending feature as part of your application by using the language-specific libraries. So here, this is an example of a Python library where we are sending event as part of application, and then we are querying the Riemann index to read back that recently sent data. Also, all the established metric collection tools like collectd, logstash, syslog-ng, they all support Riemann output. So you can actually use any of these by default. You might be wondering why syslog-ng, it's a logging system. Many a times you have a use case like you want to capture how many times this particular regex match happened in the logs and build a metric out of it. let's say you want to know how many times a particular IO exception has happened. So for those use cases, you can actually do as part of syslog ng. It's built in syslog. If there is one thing I would like you to take away from these slides, I would say the Riemann configuration. It's very unique because it's a Clojure code, and the meaning of this is you can actually leverage all the language specific features, like you can build libraries, you can divide the Clojure code into small reusable modules, you can do testing on top of code. Those all things which Clojure supports, you can actually do now apply on the config file. And this has a very unique, let's look at one of the, before that, I would like to actually show you an example. This is a Prometheus config. If you have worked with Prometheus, this is an alert expression from Prometheus. And in my job, I noticed that the Prometheus repo has these 3 configs, which are actually trying to point to the same thing. They all are trying to find whether a service is down or not. But these are written by 3 different teams, and it's different across these 3 teams. Now, this is the problem you can solve in Riemann better, because now you can write libraries. So someone who is aware of Riemann can build libraries, and other teams can just reuse those libraries. In this example, if you see that the second and third are basically not taking care of whether the matrix is not present. So let's say only the first one is taking care of the absent, using the absent function of Prometheus. So, but in Riemann, like as an SRE, I can build libraries for other teams, and they can just call those functions. This may not seem very catchy for small companies, but for big organization where there is like width of products, it is very powerful feature, I would say. This is an example of how you can basically organize your Riemann code. So in this case, we are using the Clojure namespace features. So all the configuration which is related to infrastructure are now built as a library. And then you can import this library into your Riemann configuration. So let's say you can, this is infrastructure related example. You can do, let's say if you are using MySQL, you can build a library just for MySQL related metrics, and then you can import those. This way you can organize this really well. Let's say you want to have metrics on memory, which needs to be shared across multiple teams. Like they want to know whether their applications are using more memory than what they should be. Then you can build these libraries, and these can be reused by various teams. This is another important aspect, the testing aspect. Let's say you create a pull request, making a change in your monitoring system configuration. Now, how do you test it that it works syntactically as well as semantically? In Riemann, you can make use of Clojure unit test, integration test to find whether the syntax and semantics aspect of the change is valid before pushing that to production. Another feature Riemann supports is a concept of tap. A tap is basically like a breakpoint. When you, if you have used GDB, like there, you can actually breakpoint and you can see the values. What are the values of the variables? It's exactly same. Just in this, when you create a tap, you can basically see what is the value of the event at that point of the tap. We'll look at this example. On the left side, you can see we are defining a foo stream where we are doing some filtering using the where clause. And then with clause, we are actually appending state as OK. And then we are tapping that stream. That means now you can test this stream. On the right side, you can see we have written a test where we are injecting some test event, and then we are validating that whether the output from that stream is as expected or not. So you can see that the state OK is now appended as part of the event. So this is one way you can validate your Riemann config before actually pushing it to production. Let's look at some of the usual monitoring use cases which we have to deal with in our daily life. Let's say, how do you detect whether a service has gone down? If you know about Prometheus, you write like every exporter generate metrics like up. So based on the value, whether it's 1 or 0, you can say it's up or down. Also, you need to make sure that the metric is actually present. So you need to add an absent function that metric is not absent. But in Riemann, there is a slightly different way. So if you remember, every event has a TTL as part of the event. So TTL decides how many seconds that event is valid after it has occurred. So let's say if a service stops sending events at this point, now what we will notice is that the new events are not coming and the existing events will go into expiry state. And when they get expired, Riemann basically takes them out of the index and again re-injects them to the back to the Riemann stream, but with state as expired. So if you are looking, if in your Riemann config you say that, okay, tell me all the events which are in expired state, that will give you the services which are down, basically. So you can leverage this way to find out the services which are down at the current moment. Another thing is, let's say when things break catastrophically, you get flood of events which leads to flood of alerts. This is a very usual scenario which happens. But as an SRE, if you're on call, you want to know that something is wrong, but you don't need to know that these services, every instance is of failure when things break badly. So Riemann provides two kinds of stream for handling this. There's one stream called ROLLUP. ROLLUP is basically allows you to process few events quickly and then wait for rest of the events and then batch them and send as part of one notification. So in this example, if you notice, we are doing ROLLUP 3600. So that means that the first 3 means like it will take 3 events, it will send 3 notifications at max in 3600 seconds, which is 1 hour. So what we are trying to do here is like, send me the first 2 notifications very quickly, but anything other than that, it will just batch them and send a single notification at the end of the hour. So this is one way to make sure that you don't get flood of alerts. But this has a problem because now it's batching things in memory. It can easily lead to out of memory situation. Your application may end up taking whole memory and can lead to unbounded memory usage. To prevent this, you can use throttle. Throttle is basically saying that I will accept first 3 events and I will discard anything other than that. So, but in production, you may not want to discard everything because like it is like dropping events. There might be something useful. So what you can do instead is you can use ROLLUP and throttle together to basically prevent the bad aspect of both ROLLUP and throttle. So in this scenario, we will roll up events, but we will not lead it to unbounded memory usage. It will still be bounded. Let's look at some of the edge cases which a Riemann user must be aware of. These questions come very frequently in the Riemann mailing list, so I thought it will be good. There is something called clock skew. So basically, Riemann uses the system clock to identify whether a system event has expired or not. Many a times, the infrastructure people don't use NTP or like their time goes out of sync. In that cases, let's say the client machine from where the event is being sent can go out of sync, or in different time zone, or due to daylight saving, the clocks are out of sync. In those scenarios, the Riemann can actually think that the event is expired because the time is different. So this is one scenario where people see a lot of expired events. Then there is another where when Riemann reloads its configuration, because all the state is in memory, it doesn't persist that on disk. Because of that, the Riemann can actually lose its state when we are reloading the configuration. This causes a bit of a problem because let's say you are using some time window functions where you are doing some computation on a group of events and you reloaded the configuration. That means all your state is lost, and this can cause some issues. Next, let's look at how can you scale Riemann. Riemann doesn't do any sharding. It doesn't do any of the sharding or replication. But Riemann provides a stream called forward. Using forward stream, you can actually make sure that your events are manually sharded. So you can do design systems like all the events which is coming from application X goes to Riemann X, but all the events coming from application Y goes to Riemann Y. So you can manually shard the events, but this has a problem because all the streams in Riemann are synchronous streams. That means it will wait for the acknowledgement from the upstream, and this has a problem. So let's say if this Riemann instance is sending and this forwarding the event to some other Riemann instance, it will not return the acknowledgement back to the client until it receives the acknowledgement from the upstream. And this can actually reduce the performance of Riemann. To prevent this, Riemann supports two streams. One is batch and one is async queue. Batching, as you know, you are just batching set of events together, and based on whether the batch size has filled or batch duration has completed, you can now send that to forward it to the, let's say you are forwarding the events to InfluxDB, you can use batch. Also there is async queues. Async queues are like bounded queues, let's say, but this has it will help in handling the situation where the acknowledgements are delayed, but it has a drawback. Because it's a bounded queue, that means you can end up losing the events. If you want to handle this situation, you can use disk-based queues like Kafka. Riemann supports Kafka totally as consumer and producer. So you can basically send events from Riemann to Kafka and then again consume back from Kafka. Those integrations are really well supported in Riemann. This is an example of a Riemann configuration where we are using batch and async queue together to build an efficient Riemann processing system. And with that, I would like to say thank you for attending this talk. I'm ready to take any questions you have.